Hello everyone. Today we are talking about low-rank modeling of third-order tensors. Firstly, we need to introduce what is low-rank modeling. As it is well known, in MATLAB, we store an image as a matrix. For example, in this image, this part of the image is part of a matrix, and each element of this matrix corresponds to one pixel of this image. Please look at those images. For example, pay attention to this. Pay attention to this Chinese character. So you can see this Chinese character is very symmetric. So if we represent this image as a matrix, so this matrix should have a low rank. Low rank here means that the rank of the matrix is much smaller than the number of columns. And if we look at this picture, you can see this column is identical to this column and this column. So this means if we try to use a matrix to represent this image, this matrix should have a very low rank. And if we look at this human face or this image, we know that those matrices should also have a low rank structure. The main purpose of our research is to pursue the low-rank structure in high-dimensional dataset. For example, this is a corrupted image. You can see there are lots of spots here. And the background, you can see if we can get rid of those kind of spots, the background is a low-rank matrix. People introduce robust PCA to recover the low-rank structure of this matrix. That is, we try to use a low-rank matrix to approximate the original matrix with a sparse error. So this was introduced by Candice, Ma Yi, and John White. They called this method robust principal component analysis. So their methods have lots of very useful applications. For example, so this is a video recorded in the camera of a mall. You can see the background of this video cannot change because those buildings, those settings in this building cannot change. But there are lots of people moving around. So those people moving around can be considered as sparse error. So we try to use a low-rank matrix to approximate the original video matrix. With the sparse error, you can see on the sparse error, those are the people. The main method is that we try to represent those video images as a matrix. Here we have 200 frames, and each frame we can stretch it to be a column in a matrix D. So now we have a big matrix D with 200 columns. And we can use robust PCA to separate this matrix D to be the summation of two matrices. One is low rank, one is sparse. in this way. So another application of long-rank modeling is subspace clustering. So clustering is a very useful technique in data mining. But subspace clustering is very different from the traditional clustering methods like k-means clustering. It is well known that k-means clustering is to group a dataset into is to separate a dataset into k groups, and data points in the same group are very similar, but data points on different groups are quite different. So subspace clustering uses a different point of view. We assume points come from a union of subspaces, and then we try to use the geometry of those subspaces to cluster the dataset into multiple subspaces. In this way, you can see there are three subspaces. One is red, one is blue, one is green. And there are some outliers. Now we introduce what is a tensor. Firstly, we look at this image. So this is a grid level image, and it can be stored as a matrix in MATLAB. However, if we have a video sequence in this way, of course we can store this video sequence into a matrix. But we will lose some information if we store this video sequence into a matrix, because you can see this video sequence has more than three dimensions. If we try to store this video sequence into a matrix, we will lose some very useful information. This means as the dimension of a dataset goes beyond 3 dimensions, conventional data representation as a matrix or a vector become insufficient. For example, if we consider this color image, we can store this color image as a matrix, but this will make us lose some very useful information, because the color has 3 channels, no 3 RGB channels. Therefore, it is very natural to use 3 slices to represent this color image. You can see that here we have 3 matrices, which can be stored as a third-order tensor. Now we look at this example. This is a facial image, and we know that this facial image dataset has several features. One feature is impressions, one feature is people, one feature is views. So it is very efficient to use a tensor to represent this facial image. So this tells us that it is very useful to study the tensor structure of datasets. So people study tensor for more than 100 years. And even some very famous mathematicians like Hilbert Felix Klein did some very essential research in tensors. So people have used multilinear algebra, algebraic geometry, and high-dimensional statistics to study the theoretical background of tensor research. Recently, people coming from control or optimization try to use convex and non-convex optimization skills to do tensor decomposition. And the people in computer science try to study applications of tensor in computer vision, image processing, or some other research areas. That means tensor research has become more and more important. So recently, Kilmer and Martin made a big breakthrough in tensor research. So they have considered a third-order tensor as a matrix of tubes. So this is a very important point of view because this kind of observation can lead us to discover such a new tensor singular value decomposition. It is well known that matrix SVD is a very useful tool to do matrix decomposition. However, to extend matrix SVD to tensor is a very difficult question, and people made lots of efforts in this direction. Kilmer and Martin made use of T-product to define a new tensor singular value decomposition called TSVD. And in TSVD, third-order matrix X can be decomposed into the product of three tensors. The middle one is a diagonal tensor. U and V are orthogonal tensors. And here, the star means the T-product. And T-product is a very useful algebraic structure. And for the details, we refer the audience to read their paper. By using the tensor SVD, it is very easy to solve such a tensor approximation problem. That is, given a third-order tensor X, we want to find another tensor Z, which has a low rank to approximate the tensor X. So the optimization objective function is in this way. However, here the rank of Z is NP hard to compute. So we need to use another function to approximate rank of Z. Before, people use nuclear norm to approximate the rank function because the nuclear norm is the lower convex envelope of the rank function. However, it was observed by Fazel and Boyd that there's a big gap between the nuclear norm and the rank function because the nuclear norm is to take the summation of those singular values, but the rank is the number of the singular values. So if the singular value becomes very big, that means the difference between the rank and the nuclear norm get bigger. In this way, we try to use a non-convex optimization to replace the rank of Z. That is, instead of using the tensor nuclear norm, we want to use a non-convex regularization of the rank of Z. For example, we can use the Schatten-P quasi-norm or the log determinant of the tensor Z. So why non-convex functions performs better we take this baby example. So we consider this baby example. That is, we consider only one element x. This element is positive. That means the rank of x is constantly 1. And if x becomes bigger, you can see the nuclear norm. The nuclear norm is linear. So when x become bigger, you mean when x is become a very big number m, then the nuclear norm is very different from the rank. You can see the nuclear norm is much bigger than 1. Much bigger than 1. So that means the gap is very big. So we try to use some non-convex function to shrink less the singular value. Shrink less the singular value. That is, for example, when we use the log determinant, you can see as the value of x become bigger, you can see this non-convex function grows slower than the nuclear norm. And there are several choices of non-convex functions. For example, we can use a power 0.8, and we can also use a log determinant or logarithm function to approximate the rank of x. By using the non-convex optimization, by using of the non-convex regularization, it is not hard to solve this optimization problem. For example, we can use the log determinant, and we can transform the original tensor x into another tensor in the FLIR domain. And then we can obtain an equivalent minimization problem, equivalent to this original optimization problem. And then we can solve the equivalent problem in the FLIR domain. Finally, we can take the inverse FLIR transformation to get the solution in the original domain. So this is not hard. This theorem has lots of applications. For example, if we try to extend RPCA to tensor RPCA, that is, we try to extend the recurrent of a low-rank matrix to the recurrent of a low-rank tensor, we can solve such an optimization problem. That is, we try to minimize the rank of a tensor plus the L1 norm of another tensor. We know the rank L. We try to minimize the rank of L, means we try to find the low rank component of the original tensor. And we try to minimize the L1 norm of S. That is, we try to find the sparse error. In this way, we can separate the original tensor X into the summation of L and S. L is low rank, S is sparse. So this is a typical optimization objective function can be solved by ADMM algorithm. So you can see ADMM algorithm is to iteratively solve this optimization problem. This is our experimental results. So the original image is a color image. So we can use a tensor to represent this image in MATLAB. And this is the corrupted tensor. By using tensor RPCA, we can recover the low rank component of the original tensor. And you can see the image after recovery is very similar to the original image. And you can see the result is very nice. Another application of tensor is the tensor multi-view subspace clustering. So I already tell you that the facial image data can be stored as a tensor. That is, we can group the image data into a tensor by using different views and different features. In this way, we can solve such an optimization problem. That is, we try to use x times z, and z here is a low rank tensor with a block diagonal structure. So we try to use x and z, x times z to represent x. That is, if we have a data tensor, a third order data tensor, and our purpose is to find such a self-expressive tensor z. And then by using the geometry of z, we can do the multi-view clustering. You can see our result. Our result is very nice. In the future, we try to do more and more applications of tensor low-rank modeling. For example, we can do background and foreground separation in video. And then we try to develop more and more theoretical background of non-convex optimization formulation. Thank you.